Now we have one more video from this section, and it's going to be an applied problem. No, it's not all that bad, really. You should know that the work done by a constant force in moving an object along a line of motion is given by work done equals the force times the distance it's moved. In vector format, the length of a vector times the length of the vector representing, this is like the force vector, and this would be like the length of the vector's distance moved. So if a constant force is directed along the line of motion, like if you're pushing from behind a car, then this is a nice convenient formula. But if the force isn't directed exactly along the line of motion, in other words, if the wind isn't at your back, if it's coming from the side, then we need to use how much is applied in the line of motion when we calculate work times the distance that is moved. Okay, so the formula would be this. In projection form, the work done is the length of the projection of F in the direction of PQ times the length of vector PQ. And it turns out that in dot product form, it's just the force vector dotted with the vector describing the motion of the object. So here's a question. Here's our applied problem. The wagon in the hay with hay in it picture or example, right, from before. Remember, it's 100 pounds in this thing. How much work does it take to push the wagon 40 feet up the ramp? Well, that's different from pushing it 40 feet in this direction. 40 feet up the ramp. How much work does that take? Well, you got to think of two things. The vector PQ, which is the direction vector, is 40 times this unit vector. Remember where we got that unit vector? It was cosine of 30i plus sine of 30j. So we're going to push it, this vector, I guess I got to call V here, but that's this vector PQ, right? We're going to move it 40 feet up this ramp. But the force, this vector force, is 100 pounds due south, due towards the earth. So I mean, therefore F is negative 100J. So what we want to do to calculate the work is find the dot product of negative 100J with our motion vector, which is 40 times square root of 3 over 2i plus square root of 1 over 2j. And so when you multiply this out, good gracious, because this doesn't have any I in it, it's 0i, so 0 times the 40 square root of 3 over 2 is still 0. And it's just going to be 100 times, negative 100 rather, times 40, that's negative 4,000, times 1/2, so negative 2,000 foot-pounds is the amount of work that this hay wagon is doing. That's the amount of work gravity is doing, so therefore we must do the opposite work to push it back the same direction. So we must do 2,000 foot-pounds of work to push this one, even though it only weighs 100 pounds, to push it 40 feet up this 30-degree ramp. So next time you're pushing a wheelbarrow uphill and you find that you get really tired from even fairly short distances, now you know why.